Welcome. In today's video, we're going to derive the mean and variance of the geometric distribution. Before we begin, let us first define our probability mass function for the distribution. So if x has a geometric distribution with parameter p, then we say the PMF, or the probability mass function of x, is given by the following. And I'm going to use this particular version of the PMF. There's two versions that we typically do, but I'm going to use this version. 1 minus p to the power of x times p, where x is an element of 0, 1, 2. So in other words, the random variable x denotes the number of failures before the first success, not the total number of trials. So, now that we have defined the PMF, we can find the expected value by using our definition, and the expected value of x for a discrete random variable is the sum across all values in the sample space of x multiplied by the probability mass function. For the terminals of the geometric distribution, we know that it starts at 0 and continues all the way to infinity. So we can write this summation as x equals 0 to infinity of x times, and now we can substitute in our value of the PMF. Now, in our next form of simplification, what I'm going to do here is the first thing is I'm going to recognize that the terminal, when x is equal to 0, well, this particular expression here collapses to 0 because you've got 0 times whatever expression you have here. So in fact, we can really start the terminal at x is equal to 1 to infinity instead. The other thing that I'm going to do is I'm going to take a factor of p outside the summation sign out here. And in fact, I'm going to do one more thing. I'm going to take a factor of 1 minus p outside the summation sign. And we can do that again because these particular values are not dependent on the index of the summation. So that leaves us with x times 1 minus p, but now to the x minus 1. Now you might be asking why I've done this particular expression, or why bother with this. And the reason we're going to do that is because of the following property, or the following interesting property. You see here, dealing with summations of a product of an x and then an expression here which is a power is problematic. It's not ideal. What would we much rather look at is rather a summation of a purely power series, because we know how to deal with an infinite sum of a power series, right? We have a formula for an infinite sum of a power series. So how can we make this look like a power series? We're going to do something very interesting. What we're going to do, we're going to keep the 1p, the 1 minus p at the front, and x equals 1 to infinity. And we're going to notice that this expression looks very similar to the derivative of an expression, right? Here's the minus 1 of the power, and here's the power brought down the front. And in fact, it is equivalent to this expression here, minus px. And you can pause here just to make sure that you recognize that this is the case. But again, if we were to differentiate this expression with respect to p, we'd take the x down the front, we'd subtract 1 off the power, and then of course we'd multiply by the derivative. And that derivative, if with respect to p, is just -1, and it would cancel the negative here, and we'd be left with that expression up the top. So once you're comfortable with that, we can now do some further simplification. And here is the next interesting property. When we take the sum of derivatives, we can actually, that is the equivalent of taking the derivative of the sum, x equals 1 to infinity of -1 minus p to the x, which is a very interesting expression. And in fact, I'm not going to put the negative inside. I'm actually going to take the negative and stick it out the front, because I don't like negatives in front of power series. The next part of this expression is, if you recall that we have that formula, there's a particular formula that I'm going to be interested in. Remember the sum of a power series where it's AR to the x from x equals 0 to infinity is equal to A on 1 minus R, where the absolute value of R is less than 1. Now, this is sort of the expression that I'm trying to achieve in this part here, and we're so close to it. Your value of A here is just 1, and your value of R is this factor of 1 minus P. Problem is, our terminal here is not 0, it is 1. So instead, what we can do is we can do the following. We can do a bit of an exchange. Still got the minus P1 minus PD on dP here out the front, except now we can say this is from y is equal to 0 to infinity. And just as a side note here, y is going to be equal to x minus or x minus 1. Yeah. So now what we can rewrite this expression as 1 minus p to the y plus 1 instead. We can now take a factor of 1 minus p outside the summation, and I appreciate that this is a complicated d on dp of 1 minus p sum of y equals 0 to infinity of 1 minus p to the y, and you're taking the derivative of all of that. And then, of course, now we can use our expression for an infinite series, or the sum of a power series for or an infinite power series, and it just becomes a on 1 minus r. So in this particular instance, we've still got our d on dp of 1 minus p multiplied by, now our expression becomes 1, which is our a, on 1 minus r, which is our 1 minus p. And we can close that bracket off, and we've got an expression there. And after a little bit of digging, this becomes d on dp still, or the derivative, and this simplest part of the expression simplifies to p on, well, 1 minus p over p. Finally, we've still got our minus p, got our 1 minus p. Now, the derivative of a fraction, how are we going to do the derivative of a fraction? Well, we've got two ways of doing it. Maybe I'll do it the easier way, we can rewrite this as p to the negative 1 minus 1. That's quite straightforward. And then that's equal to negative p 1 minus p. The derivative of p to the negative 1 is simply equal to negative 1 times p to the negative 2. All I've done there is power down the front, 1 off the power, negative 2. And the derivative of a constant with respect to p is just simply 0. And so now, factoring this all together, we've got negative p 1 minus p times negative 1 on p squared, and the first p cancels with the p squared in the denominator there, the negative cancels with the negative there, and we are left with the expression 1 minus p over p. And so that is a very complicated but quite simple result in the end for the expected value of x. Let's move on to the variance. Now, in a similar fashion to some of the other random variables, what we're going to do is we're going to use the property that, or to calculate the variance, we first need to calculate the expected value of the second moment, or the expected value of x squared. But to do that, we're actually going to use another property, which we know that the expected value of x squared is given by this function here. And just as a bit of a proof, in case you wanted a reminder of why this is the case, if we look at the right-hand side of the equation, which is the expected value of x, x minus 1, plus the expected value of x, this is of course equal to the expected value of, if you expand the brackets inside, you get x squared minus x plus the expected value of x. And this, of course, simplifies down because the expectation of a difference of two random variables is just the expectation of the random variables subtracted from each other. And then we've got the expected value of x here. And of course, this negative a of expected value of x cancels with this expected value of x. We're left with the expected value of x squared, which is the left-hand side. So this was just a bit of a formal proof of why this happens to be the case. And the reason that we use this is because when handling a lot of the discrete random variables, this function here, or this expectation, seems to be a little bit easier to compute than just evaluating the expected value of x squared on its own. So now that we've done that, let's just focus on that first part of the expression. So the expected value of x, x minus 1, is equal to the sum of x is an element of the support of x, x minus 1 times the probability mass function of x. This then results in the following terminals. You've still got x is equal to 0 to infinity of x minus 1 times 1 minus p to the power of x times p. From here, what we notice, or two things we're going to notice, is that when x equals 0, this expression here collapses to 0 because of the first term here being 0. When x is equal to 1, the next terminal, or the next point in the index, the x minus 1 collapses to 0, and therefore the whole expression collapses to 0. And so we can actually rewrite the terminal as just starting at 2. X minus 1. The next thing we're going to actually do is this p I'm going to bring that out the front first because it doesn't depend on the index itself. So we can take that out the front. The other thing I'm going to take out, which might not make sense right now, but hopefully it will in a second, is I'm going to take out a factor of 1 minus p squared, which means in the summation we're going to be left with 1 minus p to the x minus 2. And those who have a keen on an observant eye might notice something interesting about this expression. In particular, looks like we have a power down the front and one less off a power. Perhaps that is why. In fact, that is definitely why we have chosen this particular expression. So, in doing so, what we can do is we can continue writing p, 1 minus p squared. The sum of x is equal to 2 to infinity of d on dp of the following expression: x 1 minus p to the x minus 1 with a negative out the front. And take a moment to look at this and make sure you're happy that this is in fact true, because if we take the derivative here of this expression, the x minus 1 will come down the front, which is why you have an x minus 1 here. The new power will subtract 1, which is why you have the x minus 2. And the last thing to note is because there's an inner function here in terms of your power, you've got a minus p. So when you take the derivative of the inner function, you have to multiply it out the front, which cancels out with a negative 1, which is why you don't have a negative there. So hopefully you can see that. If you don't, take some time to differentiate this yourself and satisfy yourself that that's true. We're actually going to do the same process again. p 1 minus p all squared, the sum of x equals 2 to infinity. This time again, notice we've got an x, so a power, and a power minus 1 down the front. And so we can rewrite this as the second derivative of the following expression: 1 minus p to the x. And again, satisfy yourself that this is true. When you've got an x, what would we do? We take the x down the front, which is why you have the x. Your new power would become x minus 1. And of course, when you differentiate this, you get a negative in the inner function, and so you have to bring out a negative out the front using the chain rule, which is why you have a negative there. Now we're cooking with gas, because now, again, in a similar fashion to before, we can take out the sum of second derivatives becomes p 1 minus p squared, the second derivative of sums 1 minus p to the x. Now again, problem that we face here is the fact that our expression for x, while it's sort of looking like the sum of a power series here, we do note that we've got a terminal of x equals 2. That's a bit of an annoying thing. So what are we going to do? We're going to set y is equal to x minus 2. This then, we can transform that second expression here, d squared on dp squared. We can now write this is y is equal to 0 to infinity of 1 minus p y plus 2. Then, of course, that's taking the second derivative of all of that. And let me be clear that you're taking the second derivative of all of that. Then the 1 minus p to the power of 2, we can take out front of the summation. We can't take it out the front here because we're actually taking a derivative. You can't take out a factor when you're differentiating. That's dependent on the differentiating variable. So in this particular example, we've got 1 minus p squared, d squared on dp squared, 1 minus p squared, y is equal to 0 to infinity of 1 minus p to the y. And again, we're differentiating all of this expression, and then this becomes p 1 minus p squared d on dp squared of 1 minus p squared times, again, we already found an expression for this summation. It was 1 on 1 minus p. And then quite simply, this goes to p 1 minus p squared d squared on dp squared of 1 minus p squared over p. Now, I'm just going to simplify this slightly. I'm going to expand the top function here, and I'm going to write 1 minus 2p plus p squared, and that's just going to allow us to differentiate a little better. So, let us now differentiate this with respect to p. Let's do it one time. So 1 minus p squared. So we've still got one derivative done with, but now let's push through one derivative through this expression. We have a fraction with respect to p. So we have two options here. In fact, we have more than two options. Let's instead do this first. Let us rewrite it, dp squared, in terms of p. So the first term, the 1 over p, we could write as p to the negative 1. The second term we could write as negative 2, because it's negative 2p on p, which is minus 2. And the final term here we could write as p squared on p, or just simply plus p. And differentiating that with respect to p once gives us the following. So d on dp, let's excuse me, let's stick through one of the differentials through. So that gives us, differentiating the first expression gives us negative p to the negative 2. The second term is a constant with respect to p, so it collapses to 0. And of course the last term here is simply equal to plus 1 when differentiated, which is quite simple. And so finally here, what we get after some expansion is, again, we're going to stick through the next derivative. We'd get here a negative 2 comes out the front, so you'd get a 2p. 1 off the power here gives you negative 3, and then of course this collapses to 0, so we've just got 2p to the negative 3. This becomes p 1 minus p squared times 2 over p cubed, which after some simplification, this p out the front can cancel with the 3 there to give you 2. And then this leaves us with 2 1 minus p all squared all over p squared. Now we haven't finished just yet because we've only evaluated this first term. We need to come up with a term for the expected value of x squared. So let's do that now. We have the expected value of x squared is our expected value of x minus 1, plus our expected value of x. This, of course, becomes the expression we just found, 2p squared all over p squared plus 1 minus p on p. We derived that before. Let's do some expansion here. So that becomes 1 minus p, becomes 1 minus 2p plus p squared all over p squared. We can rewrite the second term here in terms of a denominator expressed as p squared. So p squared as well. Sorry, there's a p squared still here. So we've got a p squared still here as the denominator, so we can add like terms, though we can add numerators. If we go from p to p squared here, then we need to multiply the numerator by p as well. Following on from this, we can now do some expansion at the top. The 2 times the 1 gives you 2. The 2 times the negative 2p gives you minus 4p. The 2 times the p squared gives you plus 2p squared. We've still got that over p squared plus, and again expanding this term at the top, gives you p minus p squared all over p squared. And finally, what we can notice here is the 2. There's no terms to collect with the 2, so we've got 2 still. We've got a minus 4p here and a plus p here. That gives us minus 3p. And then finally, we've got a 2 plus 2p squared and a minus p squared here. That gives us a plus p squared, and so we can put that all over p squared still. And now we have an expression for the second moment. And now finally, after all this work, we can come up with an expression for the variance. And we know that the variance of x by definition is the expected value of x minus the expected value of x all squared. This becomes 2 minus 3p plus p squared all over p squared minus, and of course we've got minus or 1 minus p all over p, don't need the brackets at the top. That becomes all squared, which is equal to 2 minus 3p plus p squared. Let's expand the second term, p squared, minus, expanding the top function here, we've got minus 1 minus 2p plus p squared all over p squared, which is equal to, now let's do some cancellation. We've got a 2 minus a 1 gives us a 1 at the top. A minus 3p minus 2p gives us minus p, and then we've got a plus p squared minus a p squared actually goes to 0, so that is our expression at the top, and there we have it. We have an expression for the variance, just filling in that numerator down the bottom. And also for completion, let's just of course find the standard deviation of x, which by definition is the square root of the variance of x. And this, of course, becomes the square root of 1 minus p on p squared. And so there you have it. What we have done today is we've calculated the expected value of x, we've calculated the variance of x and the standard deviation of x. And one of the key techniques to be able to do this was to recognize that we could express the terms or a product of a linear function here, which is just x, and a power function in terms of a derivative. And that was the key technique so that we could express things purely as a power series, do some algebraic manipulation, and come to a result. I hope that video was informative. I hope to see you in the next one.